Hello, everyone. I am Juhi Dutta. I'm currently a postdoc at the Institute of Mathematical Sciences in India, and I will be discussing about supersymmetry from the string landscape and its prospects at the high-luminosity Large Hadron Collider experiment. And before I begin, I would like to thank the organizers for inviting me to this very nice conference. So let us begin. I would like to first state that I am a particle physicist. I mainly work on theoretical and phenomenological aspects of particle physics. So, in my talk, I will first try to give my perspective of particle physics as it stands now and why supersymmetry at all is interesting from the view of a particle physicist and what is its current status from experimental results. And then I will move on to the topic of where multiverse comes in and what are its key insights and how one can reconcile supersymmetry from the experimental results that we have as compared to the expectations from the string landscape, as well as new theoretical measures of naturalness, which compel one to redefine our expectations from supersymmetry on a whole. And then I will move on to predictions of the landscape, followed by some collider signals, which might be very interesting to look at for discovering these string-motivated supersymmetric models. So let me begin. As we all know that the standard model of particle physics is a quantum field theoretic framework, and it is currently the best description of nature. It describes the matter content and 3 of the 4 interaction forces in nature. So on the plot on the right, you see the blocks in orange. They refer to the up type, charm type, top quark, down type, strange, and bottom quark. These are the quarks in the standard model. They're charged, so these are also charged. There are also something called leptons, the most familiar of which are the electrons, followed by muons and tau, which are its heavier cousins. The leptons are charged. There are also neutral leptons, which you see here. These are known as the neutrinos, which in standard model are by construction massless. And in blue are the different force mediators. So there are 8 gluons which mediate the strong force. There is a photon for the electromagnetic force, and the W and the Z boson, they mediate the weak force respectively. And in the center in purple is the Higgs boson, which is a scalar. And in 2012, the Large Hadron Collider experiment detected such a scalar Higgs boson with a mass of around 125 GeV. And here we see a plot of one of the channels of discovery, namely in the 4-lepton final state, where I will just briefly point out that the peak in blue here represents the contribution from the Z boson and other standard model backgrounds. This peak is namely at the Z boson mass, whereas the signal peak here at 125 GeV, this is what is the contribution from the Higgs. And since they have obtained more than 5 sigma significance in this channel, one can very affirmatively say that we have found a scalar Higgs boson, which is at 125 GeV, which is around 125 GeV in mass, and standard model is experimentally very firmly established. Atlas and CMS both have also tried to measure the couplings of the Higgs boson to the quarks and leptons we saw in the last slide, and the couplings fall very beautifully on the straight red line that you see here, which is the prediction of the standard model. So all in all, standard model is very well experimentally established. However, there are several open questions that standard model cannot answer. For instance, there are a large number of free parameters in the standard model. For instance, why is the mass of the Higgs at 125 GeV? So in the standard model, it is just a parameter and there is no underlying understanding of it. Similarly, there is a huge hierarchy between the masses of the quarks and the Higgses, as well as the Planck scale. Further, there are experimental observations where neutrino oscillations have been observed, and these essentially require neutrinos to be massless. And the masses of the neutrinos are much lower than those of the quarks or the leptons and the Higgses and the tops that we see here. So this hierarchy between the different scale is not understood and is often referred to as the gauge hierarchy problem. Further, the Higgs is a scalar and it's not protected from any symmetry like the chiral symmetry for electrons. So it is sensitive to large corrections from any new particle which could couple to it. And people have tried to quantify such deviations by something called naturalness measures, which actually are very relevant in our case because we will later on see that older measures of naturalness had placed some expectations on the upper limits of the masses of the SUSY particles. But there are more refined calculations later on which redefine these upper limits to a large extent. But before we move on to that, we also talk about the fact that there is something called dark matter, which constitutes about 25% of the energy budget of the universe. And it is around 5 times that of the known matter that we see around us. And standard model cannot give us a good candidate, which can be a dark matter candidate. So one has to go beyond the standard model in order to address either all of these queries or at least some of them. And of course, there is gravity, which is not explained within the standard model. And in this context, there are various different theories. For instance, dark matter is a very pressing problem, and there are several dark matter candidates which are possible, and several theories which can provide such dark matter candidates. However, my current interest would be in supersymmetry, which is a very well-motivated model. So what is supersymmetry? It is a very special symmetry between fermions and bosons, and it postulates a superpartner to standard model particles, which differ by spin half. So on the right, you see a picture of the particle content of the minimal version of supersymmetry, which is known as the MSSM, or the minimal supersymmetric standard model. And because of the construction of supersymmetry, it requires 2 Higgs doublets instead of 1. So you have a much enlarged Higgs sector here. You have 2 CP even Higgses, 1 pseudoscalar, a pair of charged Higgses. And since they all have a superpartner which differs by spin half, they have fermionic partners here, which are known as Higgsinols. Similarly, the quarks have partners which are scalar quarks or squarks, and the neutrinos have neutrinos, leptons have leptons, and the gauge bosons also have fermionic partners. And we will later on see that mixing between these fermionic partners of the gauge boson and the Higgsinols, the lightest of them will constitute a suitable dark matter candidate called neutralino in the MSSM. So one more beautiful feature of supersymmetry is that it addresses the gauge hierarchy problem. It can also provide a dark matter candidate in specific scenarios which are R parity conserving. And it also, at high scales, it also allows for gauge coupling unification. And further extensions to its minimal version with, say, right-handed neutrino superfields can also accommodate neutrino masses. So all in all, supersymmetry is a very, very well theoretically motivated model. And coming to the mass eigenstates, so I will just quickly point out here that as we saw in the last slide, that the standard model particles have their superpartners, which differ by spin half. And so here, for instance, are listed the partners of quarks, which are squarks. However, note that here, because the top Yukawa coupling, which is the top is the heaviest amongst the quarks, so it has a larger Yukawa coupling. So the mixing in the top sector is larger. So in principle, the stops and the bottoms, they can mix, and one of the stops can be the lighter one. And this would be relevant because later on we will see that it contributes to the Higgs mass, and therefore it's a very interesting candidate to search for. Further, we have leptons and we have the extra Higgses. We have the neutralinos, which are basically the mass eigenstates are basically, there's a mixing between the neutral Bino, Vino, Higgsinols, and they lead to a set of 4 neutralinos, the lightest of which will be a potential dark matter candidate. And this can be Higgsino-like if the fraction of the Higgsino component is larger. It can be Beano-like if this is the Beano component is larger, Beano-like if the Beano component is large. So we will see some of these terms come up later. So I just wanted to point them out here. And further, the charged partners also mixed amongst themselves to form two pair of charged SUSY particles called charginos. And of course, we have the partner of the gluon, which is the gluino. So these are the mass eigenstates that we work in. And the most relevant one for us will be the stops, the lightest stop in particular, the lightest neutralino. In some cases, we will talk about Higgsino's. And in some cases, we will also talk about the second to lightest SUSY particle, or the next to lightest SUSY particle, which is the Wino-like scenario. So keeping this in mind, let us move on. And as I was pointing out, supersymmetry helps stabilize the Higgs mass. So I will briefly go through this slide. So in SUSY, we see that the first term here, for instance, is the standard model contribution to the Higgs mass coming mainly from the top quark. In supersymmetry, the partners of the top quark also add to the corrections at one loop. And what happens is that if one tries to compute this diagram, this loop diagram in cutoff regularization scenario, one will find the dependence which is proportional to the cutoff scale. And that sort of creates a problem, because then you would need to have a large amount of cancellation between this one loop correction and the tree level computation, so that one can explain the mass of Higgs at 125 GeV, which seems a fine tuning and it seems unnatural. But in the presence of extra supersymmetric partners, which are scalar-like, they provide a positive contribution to the Higgs mass, while the fermionic contribution comes with a negative sign. So there is a cancellation between these two with judicious choices of the couplings. So a Higgs mass at 125 GeV can be accommodated in the MSSM. And because it's a symmetry, in supersymmetry, since there is a fermion to boson symmetry, this cancellation occurs at all orders. So we don't have to worry so much about stabilizing the Higgs mass. And also at tree level, however, MSSM does not fit the Higgs mass correctly. So the radiative corrections are important. And a correct value of 125 GeV Higgs can be accommodated by either a large mixing in the stop sector or a light or having at least one heavy stop, which enters through this M stop 1, M stop 2, basically this product of the two stop masses here. So keeping this in mind, let us come to this diagram here, which I have referred to from this paper here, where xt essentially denotes the mixing in the stop sector. And we see that for large mixing values, which are at these peaks, in these two regions, at these two peaks, we see that one can have a Higgs mass within this particular range of 123 to 127 GeV. This range is because one has to take into account theoretical uncertainties. So one can fit the Higgs mass at large values of the mixing, and large values of the mixing would indicate having a lighter stop. And this lighter stop can, in principle, be a good candidate to look for at the experiments. Further, as I was mentioning, supersymmetry also provides gauge coupling unification for the different couplings of SU3 color, SU2L, and U1Y, and at high scales, around gut scales. And also, our parity conserving SUSY provides a dark matter candidate known as the lightest supersymmetric particle, where this quantity PR is defined in this manner, where B is the baryon number, L is the lepton number, S is the spin. If this is computed for all the SUSY particles, it is negative or -1, and for the standard model particles, it's +1. So this is important because it also dictates the fact that in collider experiments, particles, the supersymmetric particles can only be produced in even numbers. So usually pair production of SUSY particles are looked at. So keeping all this in mind, let us see what is the current status of SUSY from LHC. So before I begin, I would like to point out that these results oftentimes are presented in terms of simplified models. by which I mean that some specific decay of the particular SUSY particle is taken into account, and channels with those final states are looked into, and oftentimes the branchings can be 100%, which might not be true in the realistic scenario. So keeping this in mind, we look at the current status of these light stops, which are very important from the perspective of attaining the Higgs mass. There is a lower limit of around 1.3 TeV for a massless neutralino on the stop mass. The gluinos are also limited to around 2.3 TeV for massless neutralinos from both experiments. The electroweakinos, by which I mean the BNOs, the WINOs, the neutralinos that we were talking of before, they are also limited to around 1.1 TeV for a massless neutralino. And it's the Higgsino, however, where the Higgsino fraction is largest in the neutralinos. These Higgsino in the MSSM are compressed. And because it's always difficult to look at compressed objects, because the decay products of the heavier Higgsino to the lightest neutralino will not be hard enough to be detected at colliders sufficiently. So the compressed Higgsino sector is relatively less constrained. So one has a lower limit of around 180 GeV for a mass splitting between the Higgsino's of 0.6 GeV. So the Higgsino's are comparatively less stringently constrained from the LHC. So keeping all of this in mind, we can ask, where is SUSY hiding? Why haven't we seen anything yet? So before I go into that aspect, let me also remind ourselves that there are several issues that we have at hand. First, we were trying to understand why is the Higgs mass at 125 GeV, the gauge hierarchy problem, the naturalness problem. So that can be solved well with SUSY. There is also another issue where the cosmological constant is very tiny, which we don't understand. And there is also called the strong CP problem, which is another naturalness problem, which also exists. So all of these naturalness problems are currently something we don't understand. However, I will not be discussing so much about the strong CP problem here, and I will try to see two things: whether our expectations from SUSY so far have been correct, that we expected supersymmetric particles to be around the TeV scale in order to explain these cancellations in the Higgs mass to have reduced fine-tuning. So were our expectations correct? And also, can multiverse help understand these issues better? So before I begin on the multiverse aspect, let me touch upon the expectations of naturalness from different naturalness measures. So light stops, as I was pointing out, are a lucrative target for high luminosity LHC. And there have been various earlier measures of naturalness defined by these parameters, delta BG, which basically is this ratio where MZ is the weak scale or the Z boson mass, and Pi are the different independent parameters in the theory. So such kind of measures placed an upper limit on the stops to be around 450 GeV. And it placed an upper limit also on the mu parameter, which essentially controls the Higgsino masses. They aim to be around 350 GeV. The gluinos were also of similar order of 400 to 600 GeV, and the light and the first generation quarks and leptons are also around 500 to 700 GeV. However, for the stops and the gluinos, we already see that the LHC limit has crossed these upper limits. But there have been more refined calculations in the past decade where people have proposed something called the electroweak naturalness, which is essentially defined using this expression for the weak scale, which one can compute in MSSM. And here, delta electroweak is basically the ratio of the largest term on this right-hand side over the mz squared by 2. And using this measure, which is defined at the low scale and not at the high scale, as in the case of Barberi-Giudice, people have tried to set limits on the superpartner masses for low fine-tuning, which is quantitatively defined by this delta electroweak value less than 30. So here we see on this column that the limits for mu remain similar. However, for stops and the gluinos, the limits have increased a fair bit, and one can have a 3 TeV stop, which is still natural, whereas 6 TeV gluino can also be quite natural. And the first generation quarks and leptons, they are much, much heavier, around 10 to 30 TeV, since they don't dominantly contribute to the Higgs mass. So it seems that from the perspective of the current LHC results, we are still very much in the natural SUSY regime. Now let us try to see how these kind of limits are actually favored when one considers string landscape. And before I begin there, this is typically a picture of a natural spectra where one expects light Higgsinos, which constitute the lightest of which constitutes the lightest SUSY particle or the dark matter candidate. And these are typically in a few hundred GeV range, followed by light Vinos and Binos, which are within a TeV, followed by lightest top or gluinos, which are again within a few TeV. And the first generation leptons and squarks are all much heavier. So this is the structure of a typical natural spectra, which we will see emerges later on when one considers string landscape. I will not go into this slide. If anyone has questions more on naturalness measures, I can take it up in the discussion session. So now let's finally move to supersymmetry from the multiverse. So string theory basically requires around 10 to 11 dimensions. However, one has to compactify these extra dimensions in order to match with our observed 3+1 dimensions. So each of these compactifications can actually lead to a specific vacuum solutions, and a large number of vacuum solutions can arise from such a scenario as high as 10 to the power 500, and this constitutes the string landscape. And the string landscape essentially gives gives a proper setting where each of these vacuum solutions can actually constitute a separate universe, and the entire ensemble of which constitutes a multiverse. So this is where Weinberg also tried to explain the cosmological constant problem. So he proposed an anthropic solution to the cosmological constant problem in the multiverse of string landscape, such that there can be some universe where the cosmological constant is tiny and there is no fine-tuning problem as such. So similar reasoning can be applied to the origin of weak scale and consequently to SUSY breaking. So why SUSY breaking? Because if SUSY were not broken, then the supersymmetric particle masses would be the same as standard model masses, and we should have seen them much earlier. So there must be some version of SUSY breaking, which, however, is not the case. So supersymmetry must be broken. Now, the string theory landscape consists of a vast ensemble of n equals to 1, d equals to 4 supergravity EFTs at high scales, which contains the standard model at low scale as a weak scale EFT. And these effective field theories contain the visible sector, which could be the MSSM plus some extra gauge singlets or right-handed neutrino superfields, and a hidden sector where SUSY is broken via the super Higgs mechanism or via the F term or a D term or a combination. And Douglas et al. Actually proposed some distributions of these vacua, which are quantified by by this equation here, where F SUSY is a prior distribution, and it's proposed to be of this power law form. And here NF and ND are the number of F term and D term breaking potentials, and M hidden is the SUSY scale in the hidden sector. So, what string landscape predicts is that it shows that it shows a particular draw to large soft terms. So we try to see this using some sample values of NF and ND, say NF equals to 1 and ND equals to 0. There is a linear statistical draw to soft terms. And this is something which is very interesting because string landscape then favors large soft terms. And people have also studied supersymmetric models with low electroweak fine-tuning, which are expected to be more prevalent on the string landscape than fine-tuned models. So in this plot, what I wanted to show was these set of green points here that you see, which are consistent with the Higgs mass. So what Douglas had proposed, he had proposed a different measure of naturalness called stringy naturalness, where a higher density of such points are more natural. So supersymmetric models with low fine-tuning were expected to be more prevalent on the landscape than fine-tuned models. However, there must be other constraints to over the different pocket universes. So one has to ensure that the derived value of the weak scale in each of these universes must not be too far from our measured value, which is known as the ABDS window, which was proposed by Agrawal et al. And here is one such plot from their paper where they essentially try to talk about in more detail that if one has to explain the observed universe around us, the atoms and the chemical composition, one has to ensure that the weak scale value is not too far from what we measured. So now coming quickly to the predictions of the landscape. So using this scenario for various different values of n, where n is defined as this combination of nf2, nf plus nd minus 1, um, uh, there have been previous works which show that in n equals to 1 and 2, the Higgs mass is very close to 125 GeV. And this comes as a prediction from the string landscape. It emerges naturally, which is really nice because so far we do not have an understanding of why the Higgs mass is at 125. So this naturally emerges from the landscape. Further, the gluinos also are expected to be heavier, around 3 to 6 TeV. And for the first generation quarks, the peaks of these probability distributions are around greater than 15 to 20 TeV or 30 TeV. Whereas for the lightest top, the peaks are around 1 to 1.5 TeV or so. So these plots basically are the probability distribution of the masses of these particles. And there are also some models called the natural anomaly mediated SUSY breaking models, which I will not go into because of time, which predict that there would be light Higgsinows as the lightest SUSY particle, followed by next to lightest SUSY particle being Wiener-like. And all of this falls within the naturalness limit of delta electroweak less than 30. And in these cases, also the Higgsino sector is compressed. However, the compression is not too small. It can be within 10 to 40 GeV. And Atlas and CMS already looks for light Wiener-like scenarios, and they have placed some limits from searches from boosted jets or boosted hadronically decaying dibosons, where they have ruled out some portion of these models, which are denoted by these shaded lines. However, we try to see what kind of phenomenology can still emerge, and we see that from the stop sector, one has a mass peak around 1.5 to 1.6 TeV, which is beyond the LHC current limits. And this is interesting because it seems now that LHC has just started to look for the range of stop masses which are predicted from landscape. And these stops are mostly right-handed. So this predicts that they will have these three decay modes, and consequently, one can look for fat jet signals with a large missing energy. And performing the collider analysis, we see that this 5 sigma reach can be up to around 1.7 TeV by the end of the high luminosity LHC run. And one can reach up to a 2 sigma excess around 2 TeV by the end of the high luminosity LHC. Similarly, for the light Venus, which remain allowed from current data, one can have 3 lepton or same sign dilepton signals, which again have very nice prospects. And also there are other heavier Higgs searches, which are quite nice. And yeah, I will just leave you with this slide just to say that although supersymmetry is being currently looked at extensively at the LHC, one needs to keep looking for supersymmetry because as we see in this plot, the orange lines are the ones which are the reach of the high luminosity LHC, which is still not even half as that of the predicted naturalness range. So all in all, natural SUSY parameter space is still surviving, and one needs to do many more experimental searches. One needs to keep looking at experimental data in order to probe as much as possible of these searches. So of course, I'll come to the summary, but in the interest of time, I will just leave it at here. And thank you very much for your attention.